As we all know that computer doesn't understand human language, we have been learning till now that computer doesn't understand human language. It understands only machine language, which is also called as binary language. So today we are going to see binary language or binary number system in detail. So first thing, binary, bi means two. So it has two digits, that is zeros and ones, and this is the reason it is also called as base 2 system. It is a basic building block of all the computing devices because all the computing devices process and store data in binary format only. And all the devices, computing devices, are made up of millions of switches. These switches are also called as logic gates. We will see logic gates in the coming videos in detail. So all these switches, actually, you can imagine it like a fan switch, which has only two state, either on or off. So same way, this switches also have only two states, that is on and off. And in binary, one represents on and zero represents off. So if any switch off, that means it is zero. And if it is any switches on, that means it is representing one. Let's go ahead. Just like decimal number system, binary number system is also a positional value system, just like units, tens, hundreds, etc. So this positional headings or values are written as 2 raised to 0. 2 raised to 0 is the positional heading of the rightmost digit, that is the least significant digit or least significant bit. And the leftmost digit is the most significant bit, that is MSB. So we have to start from the least significant bit, 2 raised to 0 and 2 raised to 1, 2 raised to 2, and so on. Similarly, in the decimal number system also we can write as 10 raised to 0, 10 raised to 1, 10 raised to 2, 10 raised to 3, and so on. Here we are taking 10 in the base because decimal number system is also called as base 10 system, because we have 10 digits in decimal number system. So typically we write bits in the group of 8 bits, this binary numbers. These 8 bits are known as 1 byte. So let's see the positional heading for this 8-bit binary number. So a typical binary number will be having the positional heading 2 raised to 0, which is MSB. Then 2 raised to 1, 2 raised to 2, 2 raised to 3, 2 raised to 4, 2 raised to 5, 2 raised to 6, and 2 raised to 7, which will be for the MSB, that is most significant bit. Now, when we calculate this, 2 raised to 0 becomes 1, because anything raised to 0 is 1. 2 raised to 1 will become 2. 2 raised to 2 is 4, and so on. So we get 2 raised to 7 as 128. So let's take one example to convert a binary number to denary or decimal number. So let's take an example of a binary number which is 11001001. It is a typical 8-digit binary number. So first we will write down the number. Then we will write the positional headings and the values of these positional headings. So we will multiply the positional headings with the digits. So wherever one occurring in the digit, we will write that value, and wherever the 0 is occurring in the digit, we will write as 0, because 0 multiplied by anything becomes 0. Now, so what we will do, the final step, we will add all these digits to get the equivalent decimal number. So we get the result as 128 plus 64 plus 8 plus 1, which is 201. So The given binary number is equivalent to 201 and decimal. Now we will see how to convert decimal or denary number to binary. Usually a decimal number has two parts. So this example 16.36 has 16 as the integer part and 0.36 as the fractional part. So this two parts needs to be calculated separately in a different way. So let's see those calculations. So how to solve integer part? We will repeatedly divide this integer part by the new base, that means binary, which is 2, until we get the quotient as 0. Until the quotient is 0. We will keep on noting down the remainders after each and every division, and once we get the quotient as 0, we will note down this remainders from bottom to the fractional part. We will need to multiply fractional part by 2, that is the new base. Record the integer part if it is 1, else record it as 0. That means if I multiply 0.7 by 2, so we get it as 1.4. So in 1.4, 1 is the integer part and 0.4 is the fractional part. Repeat this 2 steps until we get the fractional part as 0. In case of a long calculation, you can multiply 3-4 times to get 3-4 digits after the decimal point. Let's take an example, and here we need to convert 35 to its equivalent binary number. So integer part is 35, and as we can see, there is no fractional part. So let's start solving. 35, we need to divide it by the new base. New base is this, to which we are trying to convert. So your 35 divided by 2, we get it as 2 17s are 34. So our new quotient is 34 or 17. So 35 minus 34 will give us the remainder, which is 1. So 17 is our new quotient. Now we have not reached, we have to keep dividing until we get the quotient as 0. So we will divide again by 2. So 2 8s are 16. So new remainder is 17 minus 16 is 1. And our new quotient is 8. So we will divide again by 2. 2 4s are 8. So 8 minus 8, the remainder is 0. Our new quotient is 4. 2 4s are, sorry, 2 2s are 4. So 4 minus 4, remainder is 0. Our new quotient is 2. 2 1s are 2. 2 minus 2, new remainder is 0. So here we have not reached the quotient 0 till now. We need to divide one more time. So 2 zeros are 0 and the remainder is 1 minus 0, just 1. So finally we have reached the state where we have got the quotient as 0, and we have noted down all the remainders after every multiplication, sorry, after every division. So we will write this remainders from bottom to top. So we get 35 in decimal is equivalent to 1000011 in binary. So let's take one more example. Convert 16.36 to its equivalent binary number. Integer part is 16, fractional part is 0.36. First, we'll start with integer part. We need to divide 16 by the new base, that is 2, again and again until we get the quotient as 0. So 16 divided by 2. 2 8s are 16. Remainder 16 minus 16 is 0. Our new quotient is 8. 2 fours are 8, remainder 0. 2 twos are 4, remainder 0. 2 ones are 2, remainder is 0. 2 zeros are 0, remainder is 1 minus 0 is 1. So we solve the integer part here. 16 is and decimal is equal to 1, 0, 0, 0, 0 and binary. Now let's start solving the fractional part. 0.36 multiplied by the new base, that is 2. So we get 0.36 multiplied by 2 is 0.72. So here we need to note down the integer part. Integer part here is 0, so we will take 0. Now this new fractional part we need to multiply by 2 again. So 0.72 multiplied by 2, we get it as 1.44. So here the integer part is 1 and the fractional part is 0.44. So we will take this integer part, note down this integer part and multiply this fractional part by 2 again. So 0.44 multiplied by 2 is 0.88. So this is the integer part, this is the fractional part. We will note down this integer part. Okay, now you can go further, multiply one more time, that is up to you, but I'm stopping here this multiplication. So we get it as 0.36 and we need to note down all these parts from top to bottom. So 0.36 and decimal is equal to 0.010. So in total 16.36 and decimal is equal to 10000.010. Example, convert 121.25 to its binary equivalent. Integer part 121, fractional part 0.25. Let's solve integer part 121 divided by 2. 260s are 120. Remainder 121 minus 120 is 1. Divide by 2 again. 230s are 60. Remainder 0. 215s are 30. Remainder 0. 2 sevens are 14. Remainder 1. 2 threes are 6. Remainder 1. 2 ones are 2. Remainder 1. 2 zeros are 0 and remainder 1. So we will note down these numbers from bottom to top. So 121 and binary is 1111001. Now let's solve the fractional part. 0.25 multiplied by the new base, that is 2. We get it as 0.5. So here we got the integer part as 0 and fractional part as 0.50. So we will note down the integer part. We will multiply fractional part again by 2. So we get 0.50 multiplied by 2 is 1.00. We will note down the integer part. Fractional part has come as 0.00. So we have already got 0.00. If you multiply further, it will again give you 0. So we have to stop here. So we will note down these numbers from top to bottom. So 0.25 in decimal is equal to 0.01 in binary. So the total 121.25 in decimal is equal to 1111001.01. I hope this video has helped you to understand conversion of binary to decimal and decimal to binary and to know the importance of binary number system. If you like the video, please click on like and subscribe the channel to be updated with the new content on this channel. Thank you.